Hello everyone, welcome to another video. If you are new to my channel, please remember to like, subscribe and share. Now what we are going to focus on in this video is circular theorem. But before we look at circular theorem, we need to review the parts of a circle, right? So here I have two circles with some of the parts of a circle. So here, you know a radius is considered to be a line from the center of the circle to the circumference. So any line from the center of the circle to the circumference is considered to be a radius. So if I draw a line from the center here to the circumference, then that would be a radius. If I draw a line from the center here to the circumference, then that line would be a radius, right? So all of these lines are radius, right? Now, let's look at the diameter. The diameter is a line that passes through the center of the circle and touches any 2 points on the circumference, as you can see right here. So for example, if I draw a line from up here through the center like that to the circumference, then that line is said to be a diameter, right? Now a chord is a line that touches 2 points on the circumference, right? As you can see here. Now the diameter is a special type of chord because it passes through the center. So therefore, if I draw a line from here to here, then that would be a chord, right? Now let's look at an arc now. An arc is just a part of the circumference between 2 points. So for example, that this point here is A and this point here is B. Then the arc would be AB, right? So it's just a part of the circumference between 2 points. Now the sector the sector of the circle is the area in between two radii, right? So it is this area inside here, the area between two radius and the circumference is considered to be a sector. Now for the segment is the area between a chord and the circumference of a circle. So this area inside between the chord and the circumference is considered to be the segment. So for example, if we were highlighting the segment in this circle, it would be this area here between the chord and the circumference of the circle. Now it is very important to bear these different parts of the circle in mind to fully understand the different rules of circular theorem. Now, the first rule that we are going to look on is angle at the center and angle at the circumference. Now, this rule is pretty straightforward, right? Now, how you identify this rule? You first identify an arc, right? So once the angle at the center is subtended by the same arc as the one at the circumference, then the one at the center is twice the one at the circumference, as demonstrated here. So you can see at the center we have 2x, and at the circumference that angle is x, right? So angle at the center of the circle is twice the angle at the circumference, right? So what this means is that if I draw a new line, a line from A, point A, to another point on the circumference, right? And call that point C, and then draw a line from point C back to B, then this angle that is created at C would have the same value as the one here at X because it is going to be half the one at the center. So since the one at the center is twice the one at the circumference, the reverse is also true to say that the one at the circumference is going to be half the one at the center. So this is going to be X as well. Now, let's look at an example. Now, let's say we have a circle over here, right? We know the center point, and the center point is this point that I just put there. And let's call this O, right? And we have 2 points on the circumference. We have a point right here, which we are going to call A. And we have another point somewhere down here, which we are going to call B, right? And we have a point on the circumference up here, which we are going to call C. So if we have a line from the center from O to B, and then from O to A, and then from B all the way up to C, and then from C all the way down to A. And we know the angle measurement of this angle. We know that the angle here at O has a measure of 120 degrees, right? And you're asked to determine the angle at C, this angle here. You want to determine this angle. Then the angle at C has to be half of this angle at the center. Why? Because they share the same arc. They are subtended by the same arc, which is BA in this case, right? So you will simply just write. So all you would do is to say angle BCA, which is the angle we want to find, is equal to angle BOA all over 2, right? And then you can work this out. What is angle BOA? That is going to be 120 degrees divided by 2. And what is 120 degrees divided by 2? That will just be 60 degrees. So we are saying that this angle here will be 60 degrees. Now, most times you are asked to justify your answer. So the answer is always, the reason, sorry, is always going to be the rule. So you would say that how you know that this angle is half that one, it's going to be angle at the center. So you would just put in bracket as your reason and put angle at the center, all right? And that would be a good enough reason, right? Now, sometimes you will have more than one lines in your circle to determine different angles, all right? Now, let's look at our second theorem. Now, angles in a semicircle. Angles in a semicircle is 90 degrees, right? So that's it. So angles in a semicircle is 90 degrees. As you can see right here, we have the semicircle, because once you have a diameter, then you have two semicircles, right? This is semicircle 1 and this is semicircle 2. Now, once you have a line from the circumference of the circle to any point, and another line from the other end of the diameter to the circumference, then the angle created between those two lines is always going to have a measure of 90 degrees. So for example, if I draw another line from A to that part of the circumference here and call that point C, and then I draw a line from B to C, then the angle created is going to have a measure of 90 degrees. And if I draw a line from B to, sorry, if I draw another line from A to a point on the circumference and call this F, and then draw a line from F back to B, then the angle created is going to be 90 degrees. And this is always true. All right. So let's look at an example. Now, let's say we have a circle, right? And the center of our circle here is this point. So we know that that is the center of our circle. And we have a line that passes through the center and touches the circumference like that. So let's put it some names on it. So let's say this is A or B, right? And then you have an next point here at C. Let's call that point C. So you have a line from A to C, and then from C back to B, right? And you're asked to determine that angle. So you're asked to find the value of angle ACB. That's what we want to determine, right? But this is not the only line there. You also have another line from point A here going towards this point over here. We're going to call it D, and a point from D going back down to B. So you're also asked to find the value of angle ADB. Right? Then all you would say is that these angles are equal to 90 degrees. Right? So these angles are just equal to 90 degrees. And the reason for this is angle in a semicircle is 90 degrees. So that would be your justification for this. So this angle has to have a measure of 90 degrees, right? And as you can see here, this rule is a special case of the first one. If you look at the center O here, the angle that is at the center O here is on a straight line. So therefore, this angle has a measure of 180 degrees. And remember, we say that once the angle at the center is subtended by the same arc, and the one at the circumference is subtended by the same arc, then the one at the circumference is going to be half the one at the center. And we can say vice versa. The one at the center is twice the one at the circumference. So since we know that the one at the center here is 180, then the one at the circumference has to be 90 there. All right. Let's look at our third theorem. So the third theorem is dealing with angles in the same segment, right? So here is the rule. Angles in the same segment are equal, right? So here, or you could view it as angles in the same arc are equal. Now we have the arc AB, right? So if I draw a line from A to B, then it will create a segment, right? So if I draw a line from A to B there, then the area in between it would be the segment, right? Now, when you look at this segment, you can see that all the angles created at the circumference are subtended by this segment. All the lines are projecting from A and B. So you can see here, if we put a point over here and call it C, right? And we call this one D and call this one E here. You can see here that the line AC and CB is drawn from the line AB, that segment there. So if you know the value of this angle, then this angle is going to equal to this one, the angle at D, because those lines are projecting from the same endpoint of the segment here, right? And also you will the angle at E will have the same measure as D and C, because these lines are projecting from the same endpoints of this segment here. So when you have this situation, the angles are equal. So let's look at an example. So let's say that you have a point right here and another point. right there, that creates a segment. So you have this area, which is the segment, right? So this is A and B, right? Now you have lines projecting. So you have some points, on the circumference. You have 1 point here. Let's call that C. You have another point up here. Let's call that D. I have a next point around here. Let's call that E, right? So what you have lines projecting from A to C, and then from C to B, creating that angle. And you have this angle, and you know the measurement of this angle. This angle has a measurement of 30 degrees, right? And then you have other lines now, lines coming from A all the way up to D, and lines from D coming back down to B. Also, you have a line from E to A, and then one from E right back to B. Now you could be asked to determine the angle at D and the angle at E. Now the angle here at D has to be the same measurement as the angle at C, since they are subtended by the same segment. So this angle will have a measurement of 30 degrees, right? And this angle at E here will also have a measure of 30 degrees. And the reason for that, these angles are subtended by the same segment, right? It is this segment that creates these angles at the circumference, right? So most times you are asked to state the reason how you know this. So I am saying that the rules are very important, because the rules are basically the reasons, right? And you could write it fancy, right? To say that angle A, C, B is equal to angle A, D, B, which is also equal to angle A, E, B, which is equal to 30 degrees, right? So as you can see here, when you use the endpoints, then the angle that you are talking about is always going to be the middle letter, right? And this little symbol in front of A is what we refer to as angle. So angle ABC, angle ADB, angle AEB, and that would be 30 degrees, right? And your reason would be angles in the same segment. All right, that's how you know, because the rule says angles in the same segment are equal. So it's just a matter of understanding the different rules. Let's look at theorem number 5. Now, theorem number 5 is about a quadrilateral, but not just any quadrilateral. It is about a special quadrilateral, which we call the cyclic quadrilateral, right? And what this rule states is that angles in opposite segment are supplementary, right? So in a cyclic quadrilateral, right, what you know is that opposite angles are going to sum to be 180 degrees, right? So as you can see here, these two angles are going to be opposite to each other, right? So what we are saying is that if you know the value of this angle, and this angle here has a measure of 120 degrees, then this angle down here has to have a measure of 60 degrees. Why? Opposite angles in a cyclic quadrilateral sums to give 180 are supplementary. Supplementary means a pair of angles that sum to give 180 degrees, right? And if we add these two angles, you can see that 60 plus 120 will give us 180 degrees. So that's what this means. And these two in green are also equal. So if this angle over here is A, sorry, not equal, the sum to give 180, and this angle over here is B, right? Then what this is implying is that angle A plus angle B must equal to 180 degrees, right? Now, let's look at a real example where we are calculating some values. So let's say that this cyclic quadrilateral, we know that this is A, B, C, and D, right? And we know this angle here. We know that this angle here is say, let's say that this angle here, and note that this is not drawn to scale. Let's say that this angle here has a measure of 30 degrees, right? And let's say that this angle right here has a measure of 80 degrees. That's all you know, right? And you're asked to determine the value of angle B, D, which is this angle here. And also you're asked to determine the value of angle C here, right? So those are the two angles that you want to find. Then what this rule is saying is that you have one of the opposite angles, right? So what this rule is saying is that angle A, B, C, which is this angle here, which is the 30 degrees, plus angle A, D, C must sum to give 180 degrees because they are supplementary. So what do you know about angle BAC? We know that value. That value is 30. So it would be 30 degrees plus angle ADC is equal to 180 degrees. Now, how can we find angle ADC? We can subtract 30 degrees from both sides. So therefore, angle ADC is going to equal to 180 degrees minus 30 degrees. Therefore, angle ADC is going to equal to 150 degrees. And the reason is that opposite angle in a cyclic quadrilateral. So how we know this? We are seeing that the reason would be opposite angles in cyclic quadrilateral, right? So that would be your reason for justifying your answer. All right, because they always are going to ask you for a reason. Now, to determine angle C now, it's the same approach to this question. So we're going to start off with what we know. What do we know? We know the angle at A. So this angle using the endpoint is just BAD. So we could say, all right, angle BAD plus this angle here at C, and we can call that BCD. So plus angle BCD is going to equal to 180 degrees because they are supplementary. Then now, angle A here is 80 degrees, so just replace that. So it's going to be 80 degrees plus angle BCD is equal to 180 degrees. Then here now, how can we get rid of the 80? We can subtract 80 from both sides. So you can see that angle BCD is going to equal to 180 minus 80 degrees. therefore angle BCD is going to equal to 100 degrees. So this angle here is going to be 100 degrees. And this one down here is going to be 150 degrees, right? And the reason would be the same. Opposite angles in a cyclic quadrilateral sums to give 180 degrees. So that's how you would justify your answer there. Let's look at theorem number 5. Now, theorem number 5 has to do with the length of the tangent, right? So what they are saying is that if you have a point out here, let's call this point that is here, C. If you have a point and you have a tangent, you have two tangents coming from that point that touches the circumference at the circle, then what they are saying is that the length of the tangent are going to equal. So let's say that this is C and this point here is X and this point down here is Y. Right? So what they are saying, if this measurement here is 5, then the measurement from C here to Y has to be 5 as well. Right? So that's all this theorem is saying. Tangent form a point outside a circle are equal. Right? So in other words, since we have some endpoint here, we're saying that XC is equal to YC, right? So these two lengths are the same. Okay. So for example, I have a tangent. So for example, I have a point somewhere. Let's start so anyway. So we have a point from here that goes towards the circumference like that, touches the circumference at a point, and then we have another tangent coming from that point that touches the circumference as well. And then we have some endpoints, so let's name them. So let's say the point, so the point right here, that point, let's call that A. And the point that it touches the circumference, let's call that B. And the point that it touches the circumference down here, call that C. So what we're saying is that the distance here from A to B is going to be the same distance from A to C. So all this rule is saying is that AB is going to equal to AC. Right? So very important rule to remember. So this one is pretty easy and straightforward. All right. So now we are looking at theorem number 6, tangent, angle, and radius. All right. Now for this one, it is just saying that the angles between a tangent and the radius is 90 degrees, right? So here we have a tangent and a radius. So the angle form is 90. That means the angle form on the other side is also 90 degrees. So that's all that they are saying to us, right? So for example, if we have another line from the center here that goes to the circumference, right? That touches the circumference at one point there. And then we have a tangent to that line. So let's say that the tangent that we have here is this line. Is a line that passes through one point there and just touches that point like that. Right? So that's the tangent there. Now the rule, what the rule is saying is that the angle created between the radius and the tangent is going to be the same, right? So this angle that is created here between the radius and the tangent is going to be 90 degrees. That's all that the rule is saying. Right? So you must always remember that when you have a radius and a tangent, the angle that forms between the tangent and the radius has a measure of 90 degrees. All right? Now, let's look at a possible example. So let's put on some labeling on this diagram. Let's say that the point here is a point F, right? Let's say the point here on the circumference is a point G. The point at the center here, that's just O. And the point down here, let's just call that P. All right, so this point here is P. So that's all that we know, right? And the only thing that they give us here is that they tell us that this angle right here at F is 40 degrees. That's what they tell us. And they want us to determine the angle right here at the center. That's what they want us to find. They want us to determine that angle at the center there. So in other words, they want us to determine angle GOP. That's the angle that they want us to find. So that's all the information that we have. Right? Now, how could we determine this angle here at the center? The first thing that would do is the ability to recognize that you have a tangent and you have a radius. So OG here is what we call a radius, right? So OG, this is a radius. Let's put R for radius. Also, OP is a radius. So your ability to identify that these two lines are radius and they meet the tangent, then the angle that is formed has to be 90 degrees, right? So the angle between the tangent and the radius is 90. Likewise, this angle here between this radius and the tangent is also 90. So in answering this question, you could write a quick statement using the endpoint to say angle FGO is equal to FGO, which is this angle here at G, is equal to angle FPO, which is also equal to 90 degrees, right? And when you make this statement now, you state how do you know that these two angles are equal to 90 degrees? Because you have an angle between a tangent and a radius is 90. So the reason would be angle between a tangent and a radius. Yes, so that's how you know that those angles are 90. Now, given the fact that you know that these two angles are 90, now let's look at the figure FGOP. That's what? That is just a quadrilateral, right? So when you look at this shape here, it's a quadrilateral. What do you know about quadrilateral? The sum of the interior angle must equal to 360 degrees. So you could write another statement now to say angle F plus angle G plus angle O which is the angle that we want to find, plus angle P must equal to 360 degrees, right? And you state your reason. How did you know that when you sum up these angles, it must give you 360 degrees? It would be what? Sum of angles in quadrilateral, right? Now, you could now proceed. What is angle F? That is just 40 degrees. So that would be 40 degrees plus G, that's 90, plus O. Let's call the angle at O. We don't know that. So just keep it as is. So that's just angle O there, plus angle P, that's 90 degrees. It's going to equal to 360 degrees, right? So it's just a matter of adding up these values. So 90 plus 90, that's going to give us 180, right? So 180 plus 40, that is going to give us 220, right? So what we know here, we're going to have 220 plus angle O is equal to 360 degrees. So it's just a matter of just subtracting 220 from both sides. So angle O is going to equal to 360 minus 220, right? And that value is going to give us what? That value is going to give us 140, right? So what we're seeing now, we're therefore seeing that angle GOP is equal to 140 degrees, which is this angle here. So this is one way you could do the question. Or another way to do the question is to recognize that, all right, this shape is a quadrilateral. So since this angle here is 90 and this angle here is 90, that's just 180. That's half of 360. So therefore, this angle at O here has to be 180 minus this angle out here, which is 40. And you would still get 140 degrees. All right. Now to circular theorem number 7, which deals with alternate segment, right? And what this rule is saying is that angles in alternate segment are equal, right? So they are equal. Now this one may be tricky for a lot of students, but I'm just going to show you a quick trick to identify this one quickly. Now, as you can see here on the diagram, we have an angle here, which is 58, right? So this angle right here is 58. And also up here in the triangle, they identify this angle to also be 58. So these two angles are in alternate segment. Now to identify the alternate segment, first, you highlight the one that the angle is in. So this angle 58 here is in this segment right here. So you can just shade the segment. It is in this segment. So the alternate segment means the other segment, right? Not this one that I highlighted, but the other one, which would be over here. So to find out which angle is equal to 58, is just look at it from an opposite point of view. So the angle that is opposite to this segment will have the same value as this angle. So if you draw a line from here, like that, the angle that is opposite to it would be this angle up here. Likewise, if you do the same thing, this angle here is given as 54 degrees, and you want to find the angle inside of the triangle, that would be 54 degrees. It also would be this angle up here that has a measure of 54 degrees. But it's just a matter of highlighting the segment and just looking at it from an opposite point of view. So the angle that is opposite to this segment is the angle that has the same measure as this angle right here. All right, so that's it. Now let's do an example. So here, over here, we're given some angles, right? We know angle PQS is given as 50 degrees. So that's what we know. Let's write out that. So angle PQS is equal to 50 degrees, right? Our job is to find the angle inside of this triangle that will also have a measure of 50 degrees. First, which segment is this angle in? It is in this segment, so just highlight it, right? So that's a segment that creates it. Now, which angle is opposite to this segment? If you draw a line like that, it will take us to this angle up here. That's the angle at T. So this angle is opposite to it. That means it will be equal. So this angle has to have a measure of 50 degrees. So what we're saying is that angle STQ is equal to 50 degrees. And how do we know that? We know that because the rule says angles in alternate segment are equal. So that would be a reason to justify why this angle is 50 degrees. Now, our next job is to find the angle inside of the triangle here that has a measure of this angle here, which is 80 degrees. And this angle here, which is 80 degrees, is just angle RQT, right? So we know angle RQT is equal to 80 degrees. We want to find the angle in this triangle that has a measure. First, highlight the segment. Since they are talking about segment, highlight the segment that creates the angle, which is this. This is the segment there. And just look at it from an opposite point of view. The angle that is opposite to it is the angle that has the same measure as this one. So that one up there. So the angle at S would be 80 degrees as well. All right. So therefore, we know that angle QST is equal to 80 degrees. How do you know? If they ask you for a reason, the reason is angles in alternate segment are equal, right? And that's it. So this theorem is about the perpendicular and the chord, right? So what is this rule saying? This rule is saying the perpendicular form from the center to the chord bisect the chord, right? So this one is straightforward. So it is saying that right here you have the center. So the center is O, and you have a chord. Let's name this chord. Let's say the chord is AB, right? So once you have a line coming from the center or passes through the center that intersect the chord, what it does, it bisects the chord, right? And when you have a line bisecting a line, the perpendicular bisector, what it does, it shears the line into equal parts. So let's say that this part here, where these two lines meets, is C. So what this is simply saying is that AC is going to equal to CB. So if AC is 7 meters, it means that from C to B is going to be 7 meters as well, right? Now, is it just that the line has to just start at the center? Let's look at another example. Let's say we have a center here, right? And I have a chord. Let's say that my chord is somewhere over here at this point. Let's put on so. So I have my center at O, I have my chord at P and Q. All right, so let's draw my chord there. Now, if I have any line, right, which is perpendicular to this, that passes through the center and come down like that, what it does, the angle that forms at this point would be 90, and the angle that forms at this point will also be 90. Likewise, this line will share the chord into equal parts. So if we put a new letter here, and let's call this point that where they intersect F. What I am saying is that PF is going to equal to FQ. So that's it. Now, does this hold true if I extend the line up like that through the circle? Yes, it does. What if I move the card closer? Would it still remain true? Yes. Let's say I move the card, come to this point there, and now the card is right there. Right? To create two new points. Let's call this R and W. Right? So these 2 points on the circumference is R and W. It still will remain true. It's still this side here will equal to this side, and that's from this. The angle at form here will still be 90. Right? So if this point that we have here is say J, that point there where the intersect is J, what I am saying is that RJ is going to equal to JW. Right? And the angle that is formed is going to be 90 degrees. And the same is true if I shift the card up here to this point, no, it still will hold true. The angle is going to be 90 degrees, right? And these lines over here is going to equal to the length of this line from where they intersect as well. All right, and I could put a stroke on this one and that one. So that is the theorem number 8, right? So remember, to properly answer questions, you need to know different parts of the circle and to be able to identify the different parts of the circle. Now, in our next video on circular theorem, what we're going to do is to look at some exam type questions. All right. Thank you for watching and do enjoy the rest of your day.